So thank you for having me. Okay, I just got a nice message that I'm recorded, which I don't mind. Thank you. So, okay, I'll first start by saying hello to everyone. I see quite a few names that I know. I would like to sort of see you in person. Now I see something which looks similar to a graveyard, a regular set of rectangles with names on them. But hopefully you are all alive and you'll get very alive in the discussion part. Coming back to the title. So when I used to be associate editor-in-chief of PAME, we were sort of joking that the longer the title, the worse the paper. And I hope I will not follow this, and it's not true for talks. And the first word can is something I often hate in papers, and I tell all my PhDs never use can, because can could be it is possible, we did this, or it is allowed, many interpretations, but I chose it here. And I take it for granted that people who have studied basics of pattern recognition and machine learning, they know that the optimal thing in almost all pattern recognition problems is based on the a posteriori probabilities of the classes you are interested in. So the word should is sure. Should the outputs of deep nets be used? Yes, that's clear from the theory. And the word can is, how far are we from this? Because in some sense, and I say this in the conclusion as well, the holy grail of recognition is to be able to model the statistical dependence between the observations, the inputs, and the classes in terms of conditional probabilities. And it seems to me that deep nets, which in my vocabulary include visual transformers, there is a chance that they will be very good models for that. So I will just say thank you to my co-authors. The work and the slides have been prepared with Milan Schulz, who recently graduated, working on the prior shift, one of the topics of the talk. Ryle, who helped me with some of the slides and data, and Lukáš Picek, who has had a huge contribution to this work, and he's the co-author of our papers on this topic. So I will first speak a little bit about visual recognition of plants, fungi, and animals, and use it as an example for fine-grained recognition. It is in some way different from other visual recognition problems, but if we think about recognition in any natural conditions, which for instance is autonomous driving, you will see the similarities. Also, these three types of environments, or plants, fungi, and animals, are interesting because there are huge amounts of data which experts and amateurs label for you. So it's a very rich source of problems. Then I'll speak a little bit about the core why to treat CNNs as estimate of posterior probabilities and what the problems are that we encounter. These are the open problems. These things are sort of, though maybe they intended to motivate research in computer vision in that direction. So first is prior shift. Then the second thing is a complex loss matrix, which means, well, when we train deep nets, we often use cross entropy because we see the non-differentiable, say, accuracy, but in many cases, you don't care about accuracy, you care about some structured loss. For instance, swapping two species of snakes when treating a person, or swapping an edible mushroom could have grave consequences, and the two types of mistakes, or the many types of mistakes between edible, poorly edible, and actually poisonous and lethal mushrooms have completely different costs. And one thing I'll not talk about is classifier combination. So if we have posterior probabilities, we know, and multiple classifiers, because for instance, in this natural world, we often have different observations. We can have an observation of the bark, of the whole tree, of a leaf, and combination of classifiers is something that is applicable in these conditions. If we have posterior probabilities, we can do that well. Then I'll talk about, I will sort of maybe mix this in with fungi and snake examples of these problems, and then I'll conclude. So I'll start with a small historical slide. which is a copy of a slide that Helmut Neven from Google at that time showed at CVPR at 2014, so 7 years back. And his main message was, well, at Google, we are working hard on recognition, visual recognition. And visual recognition is hard because also it is diverse. And he showed this sort of pie chart, which had two messages. One thing was saying that, and that's the green center, some visual recognition problems have been solved by 2014, we know that nothing is solved. You can always go for higher robustness, difficult acquisition conditions, but we had systems that in reasonable conditions worked. So at 2014, logo recognition based on worked on key points, some global descriptors for this TOTO, the whole thing, like recognition of various iconic things worked. This text reading OCR worked already. Barcode readers were, for instance, showed by some industrial people at the exhibition. So that worked. And then he was saying, okay, lots of things don't work. We were not able to read text in the wild. These simplest things, logos, things which we recognize as humans almost immediately, are very difficult. Art, featureless, complex shape, which interacts with shading, and plants and animals. And that's why I got one of the things, I used to work on some of these sort of semi-solved problems and still work on them, like landmark recognition. You can always improve this. But plants and animals were well outside of the solved world. And also you see these slices of the cakes, because the techniques used in different slices of this cake were very different, which also meant that it was quite difficult to switch from say recognition of logos into recognition of faces. So what happened until 2021? So you see that the cake has become circle. Those separating parts are, I would say, almost gone, and everything is solved using CNNs. Okay, CNN is a very broad term, but probably most, at least academic research, is centered around CNNs. Of course, in the industry, you still have things like random forests for certain applications, for maybe efficiency and because they have been there for some time and work well. But so the two things that happened in the visual recognition domain, which I'm operating in, is that the green part got much bigger, but maybe the big green part tells us that there is more in the red part that we haven't really paid attention to. And the plants and animals still stayed sort of on the border, as you will see. So it's, of course, they are subject to this second phenomenon, which means all things are now solved by deep nets, and we can actually return to the fundamentals of machine learning, which says, okay, look, we used to be discriminative because we couldn't train anything else. We had very specific algorithms. There was no hope to do a principled, theoretically justified thing, which is try to estimate the a posteriori probability and then make the decision based on that. Now, I'm not claiming that this slide is complete. There are many things, like if you think about a pile of wires if I look at a pile of cables that our sysadmin has in a box next to his desk, when you come and say, can you connect my HDMI monitor to my digital output port, he sort of goes into this box and somehow pulls it out. I don't know how he can do it, but surely no machine can do it. So there are things which are still outside even this chart, but that's not what we want to talk about. I would like to talk about some using the plant kingdom to show some problems that we could encounter and should deal with in all problems where we are doing recognition with deep nets. So sometimes you can think about recognition of plants as a standard problem. Very often when people take the photographs, they focus on one specimen, and the problem seems to be identify the species. So a single object of interest is in the image, and the problem is treated as single label image classification. So it's a mapping between the observation, that's the image on the left, and the output would be the species. That's the first thing you can, when you think about the problem. So you are not interested in localization, you assume that the object is there, and actually this image annotation or image recognition problems, which often are just a poor substitute for detection, here they are quite well modeling the situation, because the person who wants to know what the plant is will take the image, which sort of roughly segments it anyway. Now, the first thing you encounter, which is just a small complication, very small one, if you develop plant recognition app, which we have done with the Danish this fungi society. It's called Svampe Atlas, and this is downloadable on Android and on iPhones. Is that people start testing with all sorts of stuff. Okay, no big deal. The output should not be a species ID, but it should be a species ID or not a fungi or not a plant answer. So that's not a problem. Very soon you'll find out that this becomes probably the most common class that you ever encounter. So, and the other problem is that you will not know the prior probability for this class, and in your training you cannot hope that you will have a good estimate of that. So that will somehow touch the prior probability issue. Now that was things, the things are made more difficult by the acquisition conditions, which you don't have control about. So either the phenomenon is fast, some bird flies by, or an object of interest is depicted in some non-ideal conditions. So I, for instance, am not sure what I'm looking at here. So what we can expect is that we'll not be able to give a precise answer. Even more interesting case came to our attention before CVPR. So what you see there on the image on the left is some image which was hanging on a video recorded in Utah 5 years back, and it was claimed to be a UFO. And you look at the tweet, the list of tweets under this original tweet of the recording, and it says, okay, now I believe in UFOs and UFOs, and they exist, and this is a clear one, and there were calculations that this must be some object flying at 1 mile per second, a very fast one. And then we published, as it's now quite common in computer vision, the source code for our deep blur and shape recovery from fast-moving objects paper. And someone, it would never come to my mind, ran this it's like FMO is fast-moving objects, so it's like undo the effects of fast-moving, and the result is on the right, a recognition of a natural species of an animal. And the person said this is a garfalcon. I even don't know how to pronounce it, never heard it said, but okay, it exists. I checked it on Wikipedia. And so you might have to do some very, very complicated processing before you try to recognize a natural object. So therefore, the accuracy of the top one class will often be low, and one should, okay, if we are able not only to go for the argmax, that means identification of the #1 species, we need something which often is described as confidence, and we should aim for the class probability given an observation. So if we were perfectly calibrated, that's a word that we'll use later as well. If we were perfectly calibrated classifier, if we say, okay, the top one species is something with probability 73%, indeed, if we sum these numbers and average them, this should be equal or very close to the estimate of the number of errors the system is making. This also allows for something called the reject option. So for instance, if someone if an automatic system is shown a snake, which is potentially poisonous, if your probability a posteriori is quite, let's say, not close to 1, you can trigger an alarm and ask an expert to help you. So you need this. The first thing why you need a good estimate of the prior posterior probability is the reject option, maybe to call more help. Now, you'll see the data a little bit later on, but deep nets are overconfident, and they are overconfident not only on the training set, which is well known, that your outputs or softmax, which softmax is something that in principle is like a logistic regression on the feature space, and it could be treated as a posterior. You'll see that even on the test set, you'll see numbers which are much closer to 1 than the error rates would suggest. So in fine-grained visual recognition, this problem is acute because you have very large number of classes, and there is a very long tail distribution. So some classes are very rare, and very few samples are available. So in practice, you will not have what is common in various artificial data sets for competitions, that you will have a uniform distribution on your training data. There are very small inter-class differences, and the application requires a structured loss. So not 0-1 loss, 0 for I guess top 1, top 2, top 3 correctly, and I get a penalty of 1 if I'm wrong. You can get a penalty of near infinity if that's mushroom is lethally poisonous. The same with the snake. And often the loss depends on the distance in the taxonomy. So, for instance, for many snakes, they have the same type of venom, and you use the same antivenom. So, in a sense, when someone, an aid person, starts treating a person who was bitten by a snake, he doesn't need to know whether this is, as you see on the right, which of the Pantheropis genus, which species you have. It's enough to know, let's say, a rougher category, because you use exactly the same antivenom. With mushrooms, again, you don't need to know exactly which of the poisonous one it is. The decision is throw it away. But the losses of 4 different mushrooms are very different, as I'll show. One more thing which is common in these natural world problems, but think about again the autonomous, which I'm sure that of the 90 participants, fair share is working on. You have side information. So the real problem is not identify the species just given the image, but it's given the species and the side information, make your decision. So what is the side information? It could be various things. These days, it's almost always time and GPS is available. A GPS not always, but the time always. So, and the time influences a lot of things. So the time can influence the type of observation. Maybe in the darkness you see slightly different things, but I'm more about time of the year. Some animals even change their appearance dramatically. And as you see at the bottom, the time changes at least the prior. So in almost all problems, the prior probability of observing certain animals, fungi, plants differs as a time of the year function. So here we have a plot which shows the monthly distribution of observations in the Danish fungi 20 dataset, which is something that we recently published on arXiv. And you see that Boletus, which is, let's say, the mushroom which is most, say, commonly used for cooking, at least for people who collect them in the forest rather than buying them in a supermarket, peaks right now. So maybe you can go mushroom picking after the session. And And for some other, it's exactly the other way around. So now what can we do with this? It seems to me, I would say it sort of looks obvious, but history has proved many things which we thought were obvious in computer vision wrong, that we probably do not want to have a deep net, which is different for any location and every time. By the way, the description of the environment is something that is available now as well. So you have information like a type of soil, maybe you have altitude, which changes the prior probabilities, and in some cases also appearance. That's the most difficult thing. So you will have something like a domain transform. If you go up in the Alps, your this specimen that you encounter will be slightly different. You have and also you have some other images acquired in the vicinity. So if someone took a photograph of a lynx in, I don't know, say the area around Graz in the mountains, and there are lots of those images, you probably don't expect a bear to be photographed in the same location the following morning. By the way, these are practical problems, like in the Czech Republic now, somehow lynx population has a problem because because they hunt deer, and the deer hunters, they don't like lynx, so they illegally shoot them. On the other hand, from Poland and Slovakia, bears are coming across the border, so they are photo traps installed. So these are things triggered by practical problems, but I think it's a very general thing. Start to work on classifiers which can, in a systematic way, deal with site information. And the simplest situation, which we will cover, is that we only use the site information to change the class prior, and we show that this is something can be dealt with. So this is the simple thing. If you do license plates, the distribution of license plates recognition should take into account the location, but maybe the type, the appearance of the license plate, the way the letters are printed and so on, that should not change. So that's the way we treat the problem at the moment, but it's an open problem. So I'll just go to the data just to see what happened in 2014. Since 2014, very fast, that from this completely artificial environments where you had to take a sample of a certain organ of the plant, put it on a white paper, scan it. That's when I got interested in this. We really moved fast. So already in 2016, the plant identification task at the LifeLab competition had 1,000 species. So, okay, we now know ImageNet 1,000 images, 1,000 species. So that's that was moving fast into that direction. In 2017, there were 10,000 plant species, and the training was done in sort of semi-supervised or noisy label setting. So you had some part of data which were very reliable, and then some stuff coming from Google and Bing searches, and there you could get something like a product which had the photograph on top, or you can get things from herbaria, which is also labeled with the species, but it's very different than the stuff that is in the that you will observe in nature, and some other things which are somehow related to the species but not what you really want to recognize. Well, okay, we can skip this slide. And so we see that by 2018, with all this data, the organizers dared to compare with human experts on a subset of the test data, because it turns out that whereas machines can label 25,000 images in the test set without complaining, experts are not so forthcoming. Yeah, so labeling 7,000 images was a little bit too much. Okay, so the point is that, okay, if you look at this, the top experts were still the top experts, but the machines, some of our algorithms were on par with half of the experts. So like interest in 1990s, say late, in late 2020s or early 2020s, experts and machines have sort of are sort of close to each other. It's like not as in chess, because the experts need to use for certain things like open book, because they don't remember all the species in, say, Amazonia, and often if you are, it's still a little bit artificial in the sense that we have samples, images taken, but if you are a skillful person who picks mushrooms, you do all sorts of things. You smell, you see the environment, you cut through the sometimes through the mushroom to see some other things. So it's still a little bit artificial, but okay, even based on images, we are getting close. Now, it looks sort of okay, 85% recognition rate, but that's not good if you, for instance, want to use it for reliable identification of non-poisonous species. So just to see which way the difficulty goes, if you can solve 10,000 species, which you might be familiar with, let's go into something more challenging. You go for species, 10,000 species from data deficient regions. So we sort of move towards the ability to learn and recognize species with small training sets. I'm not saying we want to go for one shot or some very low number, but once you solve with large data sets, training sets, you want to solve the same problem with a much smaller one. Okay, so still, this just reminds us that from 2019, in this very difficult setting, even the experts were struggling, and the best machines were at around 40%. So this shows that on this original pie chart, plant and nature recognition is still in the red zone, and there is some work to be done. So just to get a flavor of what is happening now, again, 10,000 species, lots of data available, because people love this, and they will label new images on a daily basis at very high speed. And often this is reliable, and there are sort of very sophisticated systems. Like for the fungi, you might have people who, every person has some sort of credit and quality rating, and by agreeing with experts and so on, his rating is going up, and that's used in the automatic manual, but from your point of view, ever-growing training set. Okay, so you can see that around, still an open problem. On all of these problems, you have something like 20%, 15% error rates. Okay, so on the point, from the point of view of methods, the fungi are no different than other recognition problems. Classical deep nets were the best on the challenges, and recently, like this year, we tested visual transformers, and they seem to have two nice properties. They perform slightly better, plus they are not so biased. They're closer to calibrated state. So now let's go to the technical problems. We have the time for that. Dealing with prior shift. So let's look, even this is not nature, but this is someone preparing a competition. So one would expect it to be the other way around, but it's not. The training set distribution almost follows some sort of, it looks like exponential, but if you look at it, there's this ZIF distribution, which is very common in real life phenomena, which means that if you rank your classes for recognition according to their relative frequency, you get this, let's call it exponential characteristic, that the most common things dominate, and then you have some sort of long tail. And then for validation, or actually for the competition, the organizers give you a flat distribution. So now it should be clear that if you train a classifier on a training set, but DeepNet as well, you cannot have optimal behavior for the two situations. If you are training to have the lowest possible error rate on the training, but that's the blue distribution, And if you have a different one in the testing, you should adapt. It's not possible to be optimal for the same at the same time. You have some formulations of the recognition problem like minimax, which could make you insensitive to the change of the prior distribution, but that means you are not optimal for the given prior at which you are operating. So when you are training a deep net, you almost always go for cross entropy, which is like maximum likelihood if the labels are one hot, which is the most common thing. And indeed, the maximum should be achieved. So the function f here, which is the deep net. So the deep net is, in our case, seen as a function which tries to estimate the class CK, the class probabilities given the observation. And there are some parameters theta that we change during learning phase, and we minimize the loss with respect to these parameters. And then at test time, these are fixed typically, and we treat the F as posterior probability and go for argmax. Now, we'll need the concept of calibration. So now this notation might be quite, you might be quite unfamiliar with it. So we say a classifier FCNNX is fully calibrated when the output is seen as a vector. So maybe before I explain the formula, so we'll see the CNN as a vector that is output. Think about it as the output of the softmax, which given the observation will give you the posterior probabilities. Yeah? And the classifier would be called fully calibrated if you take different measurements close to X and you sample from the world in which you are operating, you would really see that 80% of those samples will be from the first class, 15 from the second, and so on. So what you want is that the output as a vector that's on the right side is the same as the probability of the vector for the classes. So the difference between calibration and accuracy is that in accuracy, you often just speak about the probability of the top class. So what is the argmax value? No, the value for the argmax. But a classifier can be calibrated, is calibrated if its estimates of the class probability are not biased, even if they're fairly wrong. So if I'm guessing for a two-class problem, like say identification of a user, if I'm flipping a coin and I will be saying 50-50, I'm calibrated, but I'm not very useful. But so CNNs are overconfidence, which means that if you look at the maximum in the output, so this is what we usually we output just the argmax, but the probability of the argmax given the observation is often much smaller than what is the output of the FCNN. So overconfident in the top one class means it's not top one calibrated. The full calibration, and we'll explain in a minute why we need a full calibration, means that for every class, your probability is, let's say, an unbiased estimate of the posterior. So this has been noticed in the literature, mainly not in computer vision, and people try to compare these two quantities. So the first one is accuracy. So for some discretized set of possible results, so let's say bin M. So this would be overall bins, the average, the accuracy. So this simple one says, okay, if my estimate is correct, this is y sub I with the hat. So that is correct if it's the ground truth one. And if we do this on a large set, it should be the same thing as the sum of the confidences. So this will be 0, 1, like oscillating, and this is the probability, and over the long run, they should be the same. So we can you can use some different calibration metrics have been proposed, and you can then try to minimize your calibration error, which will then help you in a certain kind of problems. For instance, now we are in the problem of prior shift. So let's say we do a reality check and run on something very similar. We do this. We take a ResNet 110 trained on CFR, a very simple problem, and now we like this plot maybe needs some explanation. So we say, okay, you take the confidence of the classifier and you histogram it, and now you look at, so what you should have, if you have confidence between, if you take all the observations where the confidence of the top class was between 0.8 and 0. No, maybe 0.9 and 1, you should have a 95% correct result. And you see that this classifier was consistently less successful, and there's a gap. Now there's no, actually it turns out that no top one result would be below 0.2 just by sort of random fluctuation. So this is a gap, and then this even quite simple ResNet is overconfident and it's not calibrated. So very simple methods have been proposed for calibration. So this is a single parameter method that only influences the softmax. It's called temperature scaling. So it's sort of rescaling. It's one parameter of the softmax. Now, people have not paid attention to this because this is monotonic in the Z, in the response of the classifier. So this is only remapping this vector of posterior probabilities, but argmax stays the same. So if you are only interested in ordering, you will not pay attention, but you should try to do that. Well, I'll argue why you should do this. So this can be done on some quite small validation set. You can minimize it with respect to various cost function. What you have in the machine learning literature, they actually go for negative log likelihood. I think we should go for something else, which we'll see in a minute. So for this small CFR, just such a small change, one parameter, you just pay attention to it, and you get something which is quite well calibrated. Now, why do you need this? So, because if you want to adjust estimate of your deep net to new priors, so you remember we had this exponential type of training, the class distribution, and we had a uniform class for uniform distribution for training. So we can assume that if we assume that the appearance of your objects in a class do not change between left, which is the training, and E is the evaluation, then we see that the probability, we can express this common thing, appearance of X given CK, can be written in two ways, using the prior probability of a class at evaluation time and the probability of X at evaluation time times the posterior. So we are really interested in this posterior at evaluation time, and using this equality, like this assumption of appearance not changing for a given class, which is still a simplification, we see that the adjustment of the posterior is quite simple. It's proportional to the ratio of the priors. Very simple. Proportional, you need some normalizing factor, but that's easy. Now, this of course works if we have probabilities. We cannot substitute this P for F if it's uncalibrated and assume it will work. So if we calibrate our classifier, life is easy if the new prior is known. So if the prior is unknown, we are in the problem of semi-supervised training, because we have to this PE of CK has to be estimated, and that was the work of the PhD thesis of Milan Schulz, which was recently defended, and that's an open problem. So this is saying, okay, and you see in your outputs and this is beyond the details I can go into, that your priors have changed, but you don't have this information directly. Yeah? So then, of course, once this is open, people notice it, you can start going more and more complex. So you have this like, let's say, a find function, and so on. So at the moment, this is from 2020, these two parameter things work very well for these guys, but they actually work on very simple problems. And if we go to the competitions, you see that, by the way, this that the bottom part shows the accuracy. So this is the CNN. If you do not adapt for the change of the prior, that's the blue curve, and the red curve, the dashed curve, is showing the accuracy if you adjust it. So of course, to adjust it means calibrate and then rescale the outputs with the new priors. So of course, some very likely classes, the most common ones, will be much less common to decide on. So you see that the difference here is maybe 4%, 5%. So maybe the better thing is to look at it, that it takes away maybe 1/4 of the error. For the fungi, it also gave us like 5%. So and if you're, it's an important part. Okay. Class priors and site information. So we show that on the Danish fungi, we have available 3 things as site information: the month of collection, the substrate, which means the soil on which this is growing, and the habitat, which would be maybe like a park or maybe forest and so on. So if we just do one thing, we separate the problem of how do we control, how do we use this site information in the classifier. We say, okay, the only thing we'll do, we will treat these things as prior probability changing. So our problem is, for the various values of H, M, and S, estimate the priors, assume the appearance the same, calibrate your classifier, and your top 1 accuracy and top 3 will go up. Now, this it seems like modest. Of course, this depends on the data itself. But if you have a 90% accuracy, which means 10% error, and you have cut 3%, this is like 1/3 of your problem has gone, and this is significant. So dealing with the loss matrix, this is the last part. So in snake recognition has significant medical importance. It disables over 400,000 people a year, kills 800,000. In India, 5 people die an hour. So there is a network of experts that are using WhatsApp application, and they are getting this type of messages all the time. Now, it's very difficult for an expert to give a very fast opinion all the time, because he might not be sort of paying attention. So we might have some sort of duty, be on call and so on. But it's interesting to do this type of thing automatically. So you get an image like that from a Nepal police station, and you say, okay, what is this? So there are in India, of course, as we said, again, we have this distribution where certain snakes are very common. So the co-distribution of prior probabilities is again this sort of exponential zip-like, and some common snakes are non-venomous, and some are venomous. And even like the numbers of the diagonal might look quite small, but if the cost of a bite is death, 1% is not a small number. So we just show 3 scenarios which shows how we should approach. And again, I've not seen this much in computer vision literature, how we should approach the problem. So I would say a master-student type of approach is, okay, use the CNN, go for the argmax, and treat if K star is venomous. The advantage of this is that you have estimated the class, and you can use the antivenom. Now, if we simplify the problem, because the problem is quite complex with the antivenoms, you can say, well, okay, get the K, which is the a posteriori probability, which would be the calibrated, again, we calibrated outputs of the FCNN, calculate the probability that the snake is venomous. So take all the probabilities of all classes, this are called here KIR, the probabilities, and sum it over venomous. And if this is more than the sum of probabilities for a non-venomous class, you will say this was a venomous snake. If there was a competition in guessing, in predicting venomous and distinguishing from venomous and non-venomous, this will clearly beat A, because A is suboptimal. Now, the case C, something which is getting close to real world situation, that this W would be the relative cost of, okay, we can make two mistakes here. We declare a venomous snake to be non-venomous. That will have a cost W, which is probably death or some serious problem. And this is if we make a mistake on the goods on a non-venomous snake, this is a needless administration of antivenom. Now, if we play with this and say this is maybe 1,000 times more expensive, your results will change. So if we look at what our current snake recognizer does, it looks to be quite okay with 2% error on the, so if 2%, 2.1% is false positive. This is ground truth non-venomous, and we declare it, we make a mistake to declare it venomous. This one is serious. And if we calibrate, this is the overlooked venomous bite. Yeah. So if we calibrate the classifier, if we are interested in argmax, nothing changes, because this is a monotonic transformation of the posterior. As soon as you start counting the venomous and like doing the case B, where you are summing up the probability of something being venomous, you see that the results are different, the errors are smaller, but with a calibrated classifier, the errors become even smaller if you sum them up. This was the artificial example where we are just like minimizing errors. This is not what you would do in practice, because in practice, the nearest approximation is what we did, we said, okay, the cost of overlooking a bite with a venomous snake. This is ground truth venomous, decision non-venomous. We give it 1,000 times higher value than this needless administration of the venom. And for the calibrated classifier, this is very different, by the way. So this looks like ridiculous. We will be administrating needlessly the antivenom to 60% of people, but will get zero error on like 3 people. This is below 0.0. 3 people will not be treated, which should be treated. Now, this looks like a ridiculous result, but if we say, what is the cost of this? So we said that this is 56 is what we want to avoid. So the cost was 1,000 for that. So the cost of the first running the loss of the first classifier is 56,000 plus this 8,000 needless. So this is 64,000. And this guy has 22,000 times 1. That was the relative cost, plus 3,000 for the overlooked dangerous situation. So this reduces the overall cost from 64,000 to something like 25. So the modeling, and of course this, as soon as you have this complex matrix, you need you'll see that the whole vector is important, not the top one, and you need to be calibrated. Now, there are beautiful data for that. I'm running out of time. We are working on it. The WHO provides the antivenoms for every single snake. This shows another phenomenon. The loss matrix is dependent on space. So not even your prior, but also the loss matrix. This is something like this. If your car breaks down in Germany, where you have a very good ADAC tow away service, it's a different affair with different costs than if it happens somewhere in Turkey, for instance. So this dependence is like through two things. One, through the availability of antivenom, and also different species could have different level of poisonous effects based on the habitat the snake lives in. So we are working towards like the full modeling of that. The probability is also time and year dependent. So at the moment, this is an open problem. We are not training new classifiers. We are modeling the location and time of year as changes of priors, calibrate the classifier, select the loss matrix. That's okay, and then try to get as close to the prior probability given the CNN. Now, I think I should probably close fast. You can contact my collaborator Lukáš Picek about the snake app if someone wants to play with this or with the data. If you write his name in Google, he comes up top. So no, and with mushrooms, the loss function is even more complex. So, but again, it's all available because people love nature. So you can really train on problems which are very serious, very similar to what you see, for instance, in autonomous driving, but with all the data. So the loss mushroom this is from a Czech site, but I provide translation of everything on the right. So the species is here in Latin, and you see that it's like edible, very tasty, edible, poor taste. So if you, for instance, put this poor taste into your food, if you are a restaurant, you can throw away the whole batch. They're edible, but poisonous if raw. So it has to be cooked long enough. Edible only if young. You have things which are poisonous and lethal. You have things with medical effects. By the way, the loss function is very different for those people who want hallucinogenic mushrooms. Yeah? So there's they have completely different loss functions of what they want to pick and what they want to avoid. Yeah. So again, complex loss function. Again, we collaborate with the Danish Swamp Atlas on an app which is doing online recognition of fungi. I will skip this. I will skip also that which says for the label data is growing on this. The GBIF is like it's Global Biodiversity Information Facility, high quality data available. And I think it's a good model for problems which we'll encounter in computer vision, even in industry, where nobody will give you the data changing. Everything is changing over time. Here, every day new data points are added. So maybe to summarize, having this probability of the class given X is the holy grail. Many formulations can be solved optimally if it's known. This index Z are all these interventions which Schlesinger with Lavach called non-random interventions. They are these locations, time of year, all this extra information. So this is actually a family of functions and you want to decompose it. I think that in computer vision, there is a huge potential of CNS for estimation of this, like treating them as priors, but it has not received attention commensurable to its importance. And we have provided two examples where you want to use all this side information as change of prior, and that can be really integrated easily into the recognition with deep nets if they are calibrated. And I think that the 0-1, like the non-0-1 losses are very common. Yeah, like killing a deer or hitting a car which is running in the opposite direction on the road is very different. And I think that application will require calibrated classifiers. So, and since it's an open problem, I'm more like talked about the calibration. I haven't introduced many methods. You can of course look for a calibration classifier and start your Google search, and that's the talk. Thank you.